In this video, we are going to recap Unit 2, which was exponents, radicals, and variation. We've already completed exponents and radicals. Now we are going to be looking at direct variation today. So just to remind you of everything we have learned so far, we went over exponent rules, rational exponents, converting rational exponents into radical expressions. With these three topics, we started with exponent rules being when you are multiplying, dividing exponents, when you have exponent raised to another power, what do you do? So we already talked about those. We've already talked about rational exponents. That's when your exponent is a fraction. And we talked about when your exponent is a fraction, what can you do with it to convert it into a radical expression? Once we had a radical expression, then we talked about how to simplify them. So that was when we looked for factors of the thing that's underneath the radical so that one of those factors was a perfect square. Then we talked about operations with radicals. That was when we were adding, subtracting, and multiplying radicals. We learned how to rationalize the denominator. That's when you have a radical in the bottom of a fraction. How do you get rid of it? We learned how to solve equations that have radicals in them. And we looked at radical functions or square root functions and how those functions are transformed, and that was very similar to the transformations that happened with quadratic functions. Today we're going to pick up with direct variation. We actually started this already. We are going to go back over direct variation, and then to finish out this unit, we will talk about inverse variation in the next lesson. For direct variation, there are three representations of any relationship. Those three representations are a table, an equation, or a graph. So we're going to look at all three representations of the relationship between x and y when they represent a direct variation relationship. So starting with a table, in order for a table to represent a direct variation, then the ratio of y to x has to be constant or proportional. So what that means is the change in y, or the differences between the y values, and the differences between the x values is constant. So what that looks like is when you take your y values and your x values, you're going to set up a ratio of y over x. So for each y value, which they are down here at the bottom and the x's are on the top in this table, we're going to look at the y value over the x value. So the first point that we have, 1 and 6, that's the 0.16, but we're going to look at the y value over the x value. So 6 over 1 is our ratio of y to x. Then we're going to look at the next one, 12 over 2, and the next one. And we're going to keep doing this for all the values in this table. So when we look at these values, if they all represent the same ratio, then that is a direct variation. So what I mean by that is 6 over 1 is the same as 12 over 2 because 12 over 2 can be reduced to 6 over 1. 18 over 3 can be simplified to 6 over 1. 24 over 4 can be simplified to 6 over 1. And 36 over 6 can be simplified to 6 over 1. So since all of these are equal to the ratio or the fraction 6 over 1, this is a direct variation. So I'm going to say this is direct since y over x is 6 over 1 for every y and for every x. Okay, let's look at another one. Right? So we want to look at y over x, right? So 14 over negative 4. Is that equal to 7 over negative 2? Is that equal to negative 7 over positive 2? and we're going to just keep going. Right? So if you're ever unsure, what you can do, I have Desmos pulled up, you can always just double check. If you don't want to spend the time simplifying these fractions, what you can do is type them in Desmos and see if they all are equal to the same value. So let's see if 14 over negative 4 is equal to 7 over negative 2. And it is. They are both equal to negative 3.5. All right, then same for negative 7 over positive 2. That's the same as negative 14 over 4. And that is the same as negative 21 over 6. Whoops. Okay, so you can see since all of these fractions or all of these changes in y over changes in x, they are all equal to negative 3.5. So this is direct. Since the change in y over the change in x, or y over x, is equal to negative 3.5. Right, option C, we're going to do the same thing. Instead of writing everything out, I'm just going to make a note of what we're doing. We're looking at y over x. So we want to see is 6 over 8 equal to negative 12 over negative 4. Automatically, these two are not equal to each other. So I'm going to make a note here. We had 6 over 8, and that is not equal to negative 12 over 4, negative 4. Okay, so since this value is 0.75, that is not equal to negative or positive 3. So that is not direct. Okay, and finally this last one. To see if this table is a direct variation, we're just going to take our change in y over the change in x. Okay, so starting with negative 2 over negative 32. Okay, looking good so far. Since all of these ratios are equal to 0.0625, this is a direct variation. Direct variation as an equation simply looks like y equals a number times x, so y equals kx. That number that's in front of x, we call that the constant of variation, so that k value here is called the constant of variation. And sometimes your equation might not look like y equals kx at first, but it can be rearranged so that it does look like y equals kx. So starting with just some of these examples that we have already done together, we just want to know if we can write an equation so that it looks like y equals a number times x. So in this first example, that's very obvious, yes, that is y equals k times x, where our k value is 6. In the second one, we have y equals 4x minus 1. So this y equals 4x, that is direct variation, but this minus 1 on the end makes it not a direct variation. So since this equation is not in the form y equals kx, that is not a direct variation. For part C, y equals 1/2 x, yes, that is y equals kx, where your k value is 1/2. Then parts D and E, both of these start out not looking like y equals kx, but we can divide that coefficient in front of the y value, that 3, can be divided on both sides, and we do end up with an equation in the form y equals kx. So yes, that is still a direct variation, even though it doesn't look like it to begin with. Same thing for part E. We have a coefficient in front of the y that can be divided on both sides, and that simply gives us a k value that's a fraction, but that's okay. So y equals 1/5 x is still in the form y equals kx, so your k value is just 1/5 for that one. Then for part F, that one looks a little bit more complicated, but we always want to check to see, can we make it look like y equals kx? So first, we want to have y on the left and x on the right. So we essentially added 15 to both sides. Okay, so we ended up with 5y equals 15x. Then we divide by 5 on both sides, simplify, and we get y equals 3x. So that is a direct variation where k value is 3. Part G, same thing. We want to know if we can get y equals some number times x. Well, first we have to get the y value on the left by itself, so we would subtract 6 from both sides. That gives us 3y equals 9x minus 6, and then we would divide everything by 3. That still leaves us with y equals 3x minus 2. This minus 2 on the end tells us that that function is not going to pass through the origin. So that is not a direct variation. It needs to just be y equals 3x in order for it to be a direct variation. And finally, we're going to look at the graph. So the graph of a direct variation is always a straight line that passes through the origin. So for each of these, we aren't actually going to be graphing a lot by hand anymore. So really what you need to do is just be able to look at the graph in Desmos and tell whether or not it is passing through the origin and that it's a linear function. So here we go. That passes through the point 0, 0. We're good. Same thing for part B. We're just going to check each one of these. That is a straight line. It goes through the origin, so that is a direct variation. And the same with those next two, but when we graph those, just notice that we went ahead and made it y equals kx. So for this one, it's y equals 2 over 3 times x. And that's what would go into Desmos. Passes through the origin. And the same process for part D. Divide by -4. The equation is y equals -1/4 x. And that is a direct variation because it passes through the origin. All right, finally, in this last example, that one actually is the opposite direction. So we have the function already graphed and we wanted to know the equation. So really all you have to do is find out, we know that it's got to be y equals kx, where k is actually your rate of change or the slope. And that is the change in y over the change in x, or the rise over run. So to get from one point to another, we had to go up 1, 2, 3, 4, 5, and right 2. So we had to go up 5, right 2. That gives us a +5 over +2.